Hello. So this is a supplement to section 3.4. 3.4 in our Larson text is second derivative test, points of inflection, intervals of concavity. So this supplement is used comparing the first and second derivative test because remember, they both tell us when we have extrema, maximums and minimums also. Okay, so we're going to identify all the extrema on the interval, first using the first derivative test, and then we're going to show how it can be used for the second derivative test as well. So let's pick a pen and get to it. So our derivative is 4x minus 2. Remember that critical numbers occur when the derivative is 0 or does not exist. This particular derivative will always exist. So we only need x equals 1/2. So remember, that means we're taking our number line, we're taking it a 1/2, and we're cutting it into two intervals. It's like we have this number line, we pluck out the number 1/2. If you've seen Kill Bill, it's like how the master plucks L's eyeball. If you haven't seen that, please ignore that comment. Okay, and we don't need this one at all, right? We don't need this section because we only have two intervals. So now I want to pick any test value that's less than 1/2, but bigger than negative infinity. I'm going to use a 0. Over here, bigger than 1/2, but smaller than infinity, I'll use a 1. And remember, these are x values. Now I'll test it in the derivative. So this is f prime at 0 equals -2, right? F prime at 1, 4 minus 2 is +2. So since this is negative, all we care about is the negative. We know that we are decreasing. And since the derivative is positive here, all we care about is the positive sign. We know that the graph of the function is increasing here. And that jives with what we know about squares, right? A square, it's a parabola. Leading coefficient is positive. We know it's leading up, so it decreases and it increases. This happens to be the vertex. And so we know that we have a minimum at x equals 1/2. Okay, so that's what the first derivative tells us. Now, the second derivative, let's put that in blue. All right, come on. And make this go away. There we go. If we look at the second derivative, notice that the second derivative, the derivative of the first derivative, is 4. The second derivative is never 0. So there's no points of inflection. Also, the second derivative is always positive. Always positive. So what does this mean? This means that the graph f is always concave up, which is what we know for parabolas. And so our critical number of x equals 1/2 is remember, concave up, it will be a minimum. So our second derivative test, there's not much to do in terms of this chart, but it's interesting to note that, even though the second derivative is super simple, it still tells us information. The point, however, remember the point on the graph, I need to, let me see, 2x squared minus 2x plus 3. Scroll down here a little bit. I want to go back to the original function. In order to find the actual point that is the minimum, I will have to evaluate at that critical number. That looks like a sigma. It's not. 1/2 squared is 1/4. 2 times 1/2 is 1. A quarter of 2 is 1/2 minus 1 plus 3. This gives us 2 and another half, so we're looking at 2.5. So our minimum point is 1/2 comma 2.5. We'll call that 5/2, just so that they're both in fraction form, and it makes a lot more sense to me when they're both of the same style. All right, so we're going to do that again, and we're going to use up different polynomials. Now, of course, I didn't use this interval at all. I should have done absolute, extrema, and yeah, it says all. I did a horrible job on that. So let's go back up here and finish it. We happen to know we have the minimum point. I'm guaranteeing this one because it's quadratic. But if we test the end values, which I guess I didn't really think about how about we do this? How about we delete that? Okay, but can I just delete the whole table? Cut. Yeah. Okay. There we go. Okay, we also should check, I know. We also should check the endpoints. F at 0 is 3. F at 3 is let me see. 3 squared is 9. 9 times 2 is 18. Minus 6 plus 3. 18 minus 6 is 12. 12 plus 3 is 15. So we see we have a maximum here at 3 comma 15. We have a minimum here at 1/2 comma 2.5. And the other endpoint is not a maximum nor a minimum. And these are both absolutes on the interval. All right, so we could check absolute and relative extrema at the same time. All right, remember this is just a generic form, so we're actually looking at g prime of x here. Let's take the first derivative. That's 6x squared minus 6. If we want to set this equal to 0, we'll factor out a 6. And we know that this leads to x values of plus or minus 1, right? When does x squared minus 1 equal 0? That's when x is plus or minus 1. So we'll have from negative infinity to negative 1 between the 1's and the other side of 1. All right, so we're going to use orange, and we'll find our test value. Any test value between negative infinity and negative 1, I'm going to use a negative 5. In between negative 1 and 1, I'll use a 0. And a number bigger than 1, I'm going to use 2. All right, so I want to know the sign. G prime at negative 5 is, well, let me see. Negative 5 squared is 25. So I'll have 6 times 25 minus 6, which is looking positive. And really, that's all we need to know. It starts out positive. Or it is the derivative is positive, so the slopes are going up. The derivative at 0. Derivative at 0 is negative 6. And that's negative. So we are decreasing, and we're thinking we have a maximum here according to the first derivative test. We have a g prime at 2. 2 squared is 4. 4 times 6 is 24. It's positive. Happens to be a positive, 18? We don't care that it's 18. We care that it's positive. So we have a maximum, and then we have a minimum. All right. Now, first derivative test definitely shows us where those are. But if we take the second derivative, g double prime of x, the second derivative is 12x, right? And so really, I'm not looking for an interval at all. I probably shouldn't even use this chart. What I'm really looking for here is what is the second derivative at -1. When the second derivative is negative, we're concave down, and so we have a maximum. So we knew that, right? So we have a maximum at -1 using both tests. Second derivative at +1, that's 12 times 1, which is positive. If it's concave up, it'll have a minimum. Let's get rid of this table. And now we can actually find the values themselves. So, and we have this interval. All right, so we have endpoints. An endpoint of x equals -2. We have what we think is a max, a critical number, at x equals -1. We have what we think is a minimum at x equals 1. And then we have another endpoint at x equals +2. So we evaluate the original function. Let's make that in black. G of -2. This is 2 times -2 cubed minus 6 times -2 plus 3. -2 cubed is -8. -8 times 2 is -16 plus 12 plus 3 is a -1. All right, so we have a point -2, -1. At the what we believe to be the maximum, right? Critical number that it's a maximum. 2 times -1 cubed minus 6 times -1 plus 3. -1 cubed is -1 times 2 is -2. Plus 6 plus 3, that's 9 minus 2, which is 7. We have g of +1. It's 2 times 1 cubed minus 6 times 1 plus 3. So that's 2 minus 6 is -4 plus 3 makes -1. This minimum is at the endpoint. They're at the same height. So we have two minimums on this particular interval. Now what do you think is going to happen here? Let's see. 2 cubed is 8. 8 times 2 is 16. 16 minus 12 plus 3, that's 4 plus 3 is 7. So we actually have two maximums. We have a maximum here and another maximum at this endpoint. We have a minimum and another minimum here at an endpoint. The critical numbers will be relative in terms of it's on any interval. Those will be maximums and minimums. But at the endpoints, remember, these are absolute. Right, we're looking at absolute maximums, absolute minimums, and they happen to match those of our critical numbers. Kind of cool. Watch for that. All right, chugging some hot tea here. See if I can keep talking. All right, let's do it again. Actually, let's get rid of our stuff first. I realized I don't need this. And I don't need it here either. And for some reason, I've decided that you have to watch me do this. I apologize. I could hit pause. I just didn't think about it. Okay. Here's how I would actually do it. So I know I'm going to be using the first and second derivative test. So here's how I would actually do it. I would take the first derivative, 3x squared plus 6x minus 9. And then I would take the second derivative. Second derivative is 6x plus 6. So what I want to do is I want to find where my first derivative is equal to 0. 0 equals, I'm going to factor a 3 out. And when I divide by 3, I will have x plus 3 times x minus 1. So I have x equals -3 and x equals 1. Now, if I was looking For points of inflection or intervals of concavity, I would do the same thing for the second derivative. But I'm not looking for that in this particular set of instructions. What I really want to know is, what's the second derivative at -3, this critical number? Well, that's 6 times -3 plus 6, which is negative. If it's negative, it's concave down. I'm thinking I'm going to have a maximum here. What's the second derivative at +1? Well, that's 6 times 1 plus 6, which is positive. Positive means concave up, second derivative, which means we have a minimum. But we could pop back here. All right, so the second derivative test is awesome, and I would use it if I didn't need to know any intervals. If I don't need to know increase, decrease, any of that stuff, I'm going straight to the second derivative test, finding what happens with my critical numbers, and going from there. But if we need to do intervals as well, and in this one we are using the first derivative test, so we need to figure out where it switches first derivative from positive to negative and negative to positive. Our test values take anything in the given interval that's right above it. I'll use 0 anytime I can. So my first derivative, the first derivative at -5. Let's look at it here. I'm going to rewrite this as 3 times x plus 2. Let's make that an x plus 3 times a x minus 1. When I put -5 in for x, that 3 is just positive. When I put -5 in here, -5 plus 3 makes a negative. -5 minus 1, -5 minus 1 makes a negative. When I multiply positive times negative, that equals a positive, and we are increasing. Remember, it doesn't matter what the number is. All we care about is the sign. I have 3 factors here. One is always positive, and the other 2 I could substitute for. So at 0, I'm not going to use the factor technique. I'm just going to take that -9 and call it negative. And so we have a maximum, which is what we assumed from second derivative test. And the first derivative, at 2, so that 3 is always positive. 2 plus 3 is positive. 2 minus 1 is positive. When I multiply 3 positive numbers in a row, I get a positive, and that's increasing, and we have a minimum here where we thought we did. So the second derivative test, many times, for polynomials at least, is a lot quicker and easier way of determining maximums and minimums. But don't forget, you do always have to come back to the original. X cubed plus 3x squared minus 9x plus 9. Since this is a cubic and there's no defined interval for it, we know that these are relative maximums and minimums. The end behavior has this function ranges from -infinity to infinity. So we would find f of -3. Remember, always the original function when we want to find the y value. Pretty stoked about doing this in my head. That's a lie. -27. That's awesome. That's 9 times 3, which is positive 27. And then another positive 27 and 9. So these two cancel each other out. 27 and 9 feels very much like a 36. So we have a point -3, 36, which is a maximum. And we have a point f of 1. When we substitute 1, right, 1 to any power is just 1. 9's cancel each other out this time. We get 4, and so we have a point 1, 4 that is a minimum. It doesn't have to be hard, doesn't have to be long. Just keep it organized, keep it straight, and it's actually fairly straightforward. I'm not going to say that E word, but it can be easy. All right, let it be easy when you can. So my first derivative, anytime I'm looking for extrema, I automatically go to first derivative. Bring down the 4. 4 halves is 2x to the third plus 6x squared. And my second derivative is 6x squared plus 12x. Let's solve. Set the first derivative equal to 0. I'm going to factor out a 2x squared. I'm left with x plus 3. Really? Really indeed. So we get x equals 0 and x equals negative 3. So we'll have from negative infinity to negative 3. Remember, it doesn't matter which order I solve them here. They have to be in number line order when we put them on our interval. Now, if I wanted to, right, I could do a quick little test over here. And we could see that the second derivative at 0 is 0, and it's inconclusive. When the second derivative is 0, it doesn't give us any information. We're not entirely sure what's happening there yet. But the second derivative at 3, that's 6 times negative 3 squared plus 12 times negative 3. That's a 12, not a 2. Negative 3 squared is 9. 9 times 6. 9 times 6 is 36. We are inconclusive again. There's some shenanigans going on in this graph. Look at that. All right, so we come back and we'll do some test points. Let's use an x equals negative 5, x equals negative 1, and x equals positive 1. The value of the derivative at negative 5. Notice how this first piece will always be positive. And negative 5 plus 3 is negative, and when I multiply the two, I get negative, and this is concave down. All right, the first derivative at negative 1. This is positive. Negative 1 plus 3 is positive. Positive times positive equals positive, and we see that we actually do have a minimum. So the second derivative test was inconclusive at negative 3, but the first derivative test gives us information. And we'll try f prime at 1. That is positive times positive, and that's positive, and it's increasing again. So decreasing, increasing, and decreasing. Now, I don't know about you, but I'm always curious, right? When we get something like that, it's not the normal pattern. It's not the usual. So let's pull up a calculator here. I'm going to pull it over onto our screen. Let's take a look real quick at the graph of 1/4 x to the 4th plus 2x cubed. And take a look at that graph. Let's zoom out. Okay, so we can see there's going to be a minimum down here at negative 3. I'm going to zoom back in because I don't like how that looks. Here at 0, we see it gets to be a flat spot. The derivative, right, the slopes, our graph is decreasing. We have a minimum here at negative 3, as we suspected. And then this little flat point, not a maximum or a minimum, but it is a critical number. Everything looks exactly as we thought it did. I should have used the graph, but I didn't, and I just made it go away. If I want to find the value of that minimum, I will substitute it into the original. And get, okay, negative 3 to the 4th is negative 81. Negative 3 cubed is negative 27. Negative 27 times 2 is a negative 54. Bringing that calculator back. Okay, negative 81 fourths minus times 4. So that's 216 fourths. That's 297 over 4. That is a negative. Yes, a normal person would probably put that into a decimal. But if you know me, you know I'm not normal. Okay. All right. Are we finished yet? Last example. I get stressed because these videos are so much longer than my other ones, but that's because this is supposed to be class, and class is 50 minutes. Okay. Here we go. Last one. First, start with our derivative. Chain rule says we take the 2/5 on the outside, leave the inside alone, subtract 1 from the exponent, and then multiply by the derivative of the inside. Notice that's no big deal. However, I am going to rewrite this a little bit. Now, as I'm solving, I'll want to use this. That's not a K, that's an X. It looked like the K from the Yakult bottles. It's not milk, but it's a dairy of some sort. Yak milk. I think it's yak milk. Yakult. That totally. Yak. Yeah. It's been a long week. In order to solve, I'll use this. In order to find the second derivative, I'm using this version. That 1 is irrelevant to us, but we use the chain rule again. And the second derivative, we bring down that negative 3/5. We leave the inside alone, and we subtract 1 from the exponent. Don't forget to multiply by the derivative of the inside. And then, of course, we're going to write a simplification for that. That is negative 6 over 25 times x plus 1 to the 8/5. Now, you're looking at this thinking, all right, Tuesday, can we be done? Maybe that's just me. Notice that this first derivative is never 0. Anytime you set a fraction or a rational expression equal to 0, it's only 0 when the numerator is 0. And 2, my friends, is not 0. If you only have $2 in your bank account, the ATM thinks you have 0, but you still have 2. So the only issue here is we have a negative 1 that is h prime of negative 1 does not exist. So we have something happening there, and we have to figure out what that is. So let's do that. Negative 1, but notice we can't test h double prime of negative 1 does not exist either. So our second derivative test is not helpful. So any test value in here, let's use negative 2, let's use 0. I'm going to test this down below in a little bit bigger box. H prime of negative 2 is 2 over 5 negative 2 plus 1 to the 3/5. All right, talk it out with me. Negative 2 plus 1 is negative 1. Negative 1 to any power, because we don't have a even denominator here, so a fifth root, it's cool. We cube negative 1, we get negative 1, then we take the fifth root of negative 1, we get negative 1. Negative 1 times 5, this is negative. So we should be decreasing in this region. Here at h prime of 0, at 0, we get 2 over 5 times 1. So that's positive. So we're increasing. And so we're thinking here at negative 1, the original function is defined, so we probably have a minimum there. But since we have a closed interval, right, we use an endpoint of negative 2, a critical number of negative 1, and an endpoint of 0. And we evaluate the original function. So we'll have negative 2 plus 1 to the 2/5. That's negative 1 to the 2/5, which is negative 1. h of negative 1, remember this is the original function, negative 1 plus 1 to the 2/5, that's 0. Supposedly this was a minimum though. Weird. I'm going to have to look at this graph. H of 0, 0 plus 1. Negative, positive, that should be a minimum. That's so weird. Okay. It doesn't look like this critical number is the minimum or a maximum on this particular interval. And it's kind of freaking me out. So I thought we'd pop this back up here again. Let's take it over here. Go back to y equals. And put in x plus 1 to the power of 2/5. Remember, if you don't have the pretty print format, it's what it's called when you could see it in the exponent. If yours just shows this caret, make sure you put parentheses around the 2/5. Uh-oh. Tuesday can't evaluate. We do have a minimum. And so I'm glad I looked, because right here is where I screwed up. Negative 2 plus 1 is negative 1 to the 2/5. What happens when I square negative 1? I get 1 to the 1/5, which is 1. So this is a max. Here's a min, and here's a max. It's the arithmetic. I'm telling you. Once you get your algebra down, I guess powers, that's probably algebra. That's all it comes down to. Was calculus hard? No. Was evaluating the function the hardest part for me? Absolutely. Hey, sorry this is a little delayed. A little is 6 days. Check out the email. I'm going to be sending some messages soon. Thanks for listening, if you did.